The traditional way is just look at a frequency model and kind of make your predictions based on that. The Bayesian statistic is maybe we should use, if we have some other information, we should use that into our estimate. If we have, so that's back to our question that we talked about Bayesian statistics. How much of the time if you get new information will you change your mind? So we might have other estimates for our statistics based on other knowledge. Again, we have incomplete knowledge. We're just trying, statistics is trying to make use of what knowledge we do have to make a conclusion about something bigger. So for example, I don't want to use that example. I'm thinking football. I kind of use sports too much. So just kind of play along with me here for the sports one. You know that this person comes up, he bats 300, he's going to get a hit 30% of the time. But then you have some other additional information that his wrist is broken. Does that change your probability of whether he's going to get a hit or not?
Yes.
What if it's you think his wrist is broken? These are the kind of issues that are taking place now, and that's kind of where there's this sort of sometimes overhyped battle between Bayesian statistics and classical statistics. Because if you know something about the situation, why not use it to make your prediction or to come up with your estimate for your parameter? We'll kind of see that today. So there's three kind of goals. You take a sample and you estimate your statistic. To try to estimate your parameter. So you take some number, you do something with it, divide, multiply, add, subtract, those kind of things. So the question is, how do we get a point estimate for theta hat? That's question number one. Question number two is, once we get one, how do we assess it as far as how good is it? And the third one is, which one is the best? The first question, how do we get a point estimate? Well, we're going to do that in section 6.2. That's on Wednesday, so that's not today. Question number 3, which one is best? That's an entire semester-long course. This is where the statistician starts really making their money to determine which is the best statistics. And so today is, once we get a statistic, how do we assess it? So this is what this section is. So first of all, you have the distance between your estimate and the true parameter, whatever it is. And what we're going to do is use this by the squared error loss function. All right, so that's one thing that we'll just mention. You don't have to know necessarily. It kind of goes back to our Pythagorean theorem, or from our least squares method. We take our true parameter, take our estimate, and square the differences. Remember when we did this game when you try to find the countries, largest countries in the world, and we kind of took your ranking and then we squared it? This is the same kind of idea. You get penalized the further parts you are away. And it also comes back to the Pythagorean theorem. And so this distance is going to vary because this undersampling statistic varies. To assess this, we're going to need to have three kind of ideas. One is the risk function. And we're also going to need the bias function. So we're going to need the risk function and the bias function. So the first one is the risk function. And it should kind of have the same sort of pattern that you might have seen in some other ones. This is just going to be the expected value of our parameter minus theta hat squared. So that's our risk function. What we would love to have is that our risk function is 0 for every theta that we have. For every parameter theta we have, we get 0. That's not possible. Even those things that we believe are deterministic functions are not quite deterministic functions. Like if you drop something, we believe it should fall at negative 9.8 meters per second squared. But there are other sort of variations in terms of wind resistance and other things that go on that does not follow exactly like that. Even our ideal gas law is ideal. There's some other factors that go into the gas law. So there's some variation. And from those of you who are physics and engineers know that when you measure, there's always measure error. One hopes that that measure error is Gaussian distributed, which is another fancy name for normal distributed, yeah. Okay. So we can't get this. So the idea then is to make this risk function as small as possible for all theta. That upside down A stands for all, in case you wanted to know that. So we want to make this as small as possible. So we have two definitions. One is we have an unbiased estimator if and only if, or if on average we take all possible random samples and take the theta hat, that we get theta itself. So for example, the sample mean is an unbiased estimator for the mean. On average, our sample mean will estimate our true population mean, or our true, our mean. Then the other one is this bias function. And this one is that the bias function of theta hat of theta, so this is your statistic estimating your parameter theta, is going to be equal to the difference between the expected value of your theta hat minus theta. So if this is unbiased, what is your bias equal to? 0, right? I mean, because these two things will be equal, and you'll have this. So the theorem then and again, this is from the statistics part, not from the sampling method part. The theorem then is that your risk function can be split up into two different parts. Your risk is equal to two different parts. First of all, is the variation of theta hat plus your bias function squared. So you're breaking up in two parts, sort of like a Pythagorean theorem kind of idea. Let's go ahead and do the proof. Hopefully, I'll get the proof correctly. And I think the key for me is to start on the right-hand side and get to the left-hand side. So we're going to start with the right-hand side, the variation of theta hat plus b theta hat squared. So we might as well go ahead and write e to the theta hat minus theta squared. What's our formula for the variance of a random variable? Like variance of x is equal to, yeah.
Expected value of x squared minus expected value of x.
Right, so this is the expected value of theta hat squared minus the expected value of theta hat squared. This, on the other hand, will be the expected value of theta hat squared minus 2 theta e to the theta hat plus theta squared. Do you have anything that cancels off? So this one and this one? Okay. And knowing your great algebra skills of being able to use, instead of x and y, you use e to the theta hats and other things. What do I have left? This minus this times this. I can factor that as what? 1 minus the other squared?
Yeah, so e to the theta squared minus theta squared.
Like that.
That's what
Okay. And what is this? Is the risk function, right? Almost, except for what did I do with my thetas? Oh, I can bring it out.
How does that work? Because that's not on the far left, the expected value of theta hat squared, that's all in one, so that whole term isn't actually squared.
Is that the 9 minus 2 theta e theta? Is that supposed to be squared inside of it?
Okay, so let's answer go left to right for me, right to left for you. So what was your first thing, Tegan?
The far left term, that is just the power of 1. So we can't factor that. Because that's not e to the theta hat times
I see.
theta hat.
So you're saying I'd still have e to the theta hat squared. Here, though, is theta a statistic or a parameter? So I could have this as minus 2 e to the theta hat. And then theta squared could be e to the theta squared. And then this could be equal to expected value of theta hat squared minus 2 theta hat plus theta squared. Are you okay with that?
Mm-hmm.
Just because remember, theta is a parameter and not a statistic. Theta hat is a statistic, so I can't bring the theta hat out of anything. And so therefore I get e to the theta hat minus theta squared, which is equal to the risk function. Jeff, have a question?
Oh, so they're saying, because the parameter runs, you can treat it as a constant.
You can treat it as a constant, that's right. Right. Sort of like the force of gravity. It's not really constant, right? Go to Mars, it's different than where it is. Now, the key part of this, though, is interpreting this. The variance is the what we would refer to as the precision. Whereas the bias is to the accuracy. So let's see if I can draw a picture here of something. So suppose you had a bullseye. Here, this is very precise, but not very accurate. Okay, this is accurate, but not very precise. On average, I get the bullseye. But it doesn't, there's not a tightness to it. So that's got to kind of keep the difference between accuracy and precision. Precision means I have a small variation. Accuracy, on average, I'm going to get the bullseye. I'm going to get the right amount. So that brings us to the standard error, which is the square root of our variance of my statistic. That's why I'm always talking about the sampling distributions as a standard error. The standard error of the sampling distribution for X bar is the standard error, or sometimes we'll have for the t distribution, the standard error. It all comes back to that. Let's just draw one more picture here. Sometimes you have a point estimate and a point estimator. And which estimator, when used on other samples, will tend to produce the sample close to the value. Now, in the best of all possible worlds, they'll always turn out to be our parameter. But you always have some error of estimation that must happen. So the unbiased estimator is if the expected value of theta hat is equal to theta. If it's not equal to that, then the bias is the difference between that. So it's centered. Now, let's take a look at two different examples. All right, so just ignore this one on the left or right, and let's take a look at the one on the left. Here we have two estimates for theta. Okay, here's the theta is right here. Here's my estimate by theta 2. Here's my estimate for theta 1 hat. Which is the one that's unbiased? Don't look at this one. Look at this one. Which is the one?
It looks like theta 2.
Theta 2 hat is unbiased because it's right symmetrical about the true parameter. Theta 1 hat is biased, and so this difference, the average of theta 1 to this, will give me my bias of theta 1 hat. That's how far off on average I would get. Okay? Now let's try example number 2. Here we have a skewed right example. So the mean of theta 2 hat would be theta, and then the mean of theta 1 hat would be about here. Which is the unbiased estimator then? Theta 2 hat, and theta 1 hat is biased, and the difference between its center and the true parameter would be what we call the bias of theta 1 hat.
How can you tell which one is biased?
Well, you have to kind of think of is that theta is the true parameter.
Oh, okay. And the one not.
And this is just all your different sample, whatever sample theta hat you get. And so its center matches up with the true parameter.
So that one's unbiased.
Yeah, that's an unbiased estimator, right? All right, let's take a look at some unbiased estimators. For example, the expected value of our proportion, which is the number of successes over failures, gives us our P. So this our proportion is an unbiased estimator for the true proportion. Our sample proportion is estimated for the true proportion. And no matter what the true value is, the distribution of my estimator, if I could play God and do it all over and over again, on average, it will give me my P. Let's give you an example of one that's not, let's skip that one. That's kind of fun, but. Let's give you an example of one that is biased. So S squared, the variance, sample variance, is an unbiased estimator for the population variance. But remember, our sample standard deviation is given by, okay, we take the differences between my means and I divide by n minus 1. That's why we take the sample standard deviation is divided by n minus 1, because this then becomes an unbiased, the sample variance becomes an unbiased estimator for the population variance. And there's an example in your book that goes through this calculations. Unfortunately, S is not an unbiased estimator for sigma, but for the variances, this is why you divide by n minus 1, so that it becomes an unbiased estimator for sigma, which is where you divide by n. You can do all of the values. So on average, the sample variances will average out to be the true population. If you divide it by n, this would underestimate the population variance, which is why we divide by n minus 1. Alex?
Wait, so can you point to where that's explained in the text, or?
Sure. Page 245. I mean, I had this all ready to go, but I think I'm going to move on. I think the important part. You take the expected value, here's your sample variance, you end up being that you do get sigma squared. If you didn't divide by n minus 1, you would not get sigma squared. You'd be off by n plus 1 over n.
Okay.
All right, so let's suppose going back to we want to estimate the average age of Taylor faculty. Suppose that we just take a sample and we take that sample mean. That's going to be our estimate for the Taylor faculty. Suppose, though, that I have some inside information that I was working like as a temp 2 years ago, and I think I remember seeing that the average age was like 55 or 56. Would you take that information in to estimate the average age of the faculty or not? Maybe. Maybe there's enough retirements that's all messed up. Maybe we hired old people. So if we have new information, do we take that into account or not? So what this is going to do is we're going to do a weighted average of mu hat, where alpha is going to be our weight. It's going to be between 0 and 1. And it's going to be, I'm going to take the old regular sample mean, and I'm going to take like how much I'm going to say 57 is, and I'm going to calculate the bias function based on that. So first of all, let's calculate what the expected value would be. Remember, this is not, so alpha is we're going to fix it. And so the expected value of mu hat is going to be equal to alpha times the expected value of x bar plus the expected value of 1 minus alpha times 57. Well, what's the expected value of x bar? Mu. And what's the expected value of 1 minus alpha 57? Well, it's just a number, so yeah, 1 minus alpha 57. So that's that part of it. Let's take my variance of u hat. This will be alpha times my variance of x bar plus my variance of 1 minus alpha 57. What's my variance of x bar going to be? What's the variance of the sample means? Sigma squared over n. So I get alpha sigma squared over n. And what's my variance of a constant? There's no variation, right? It's just a number, so that variance is 0. So my standard error of u hat will be equal to the square root of alpha sigma over the square root of n. Just the square root of my variance parts. And so finally, my risk function, actually, this is my estimate mu hat of mu, is going to be equal to my variance of u hat plus my bias function squared. So my variance is alpha times sigma squared over n. My bias function is where if I subtract this minus mu, right? So I've got my expected value. My true value here is mu. How could I rewrite this a little bit nicer? Like combine the mu's together. Well, let's write it as expected value of mu hat minus mu squared will be alpha sigma squared over n plus alpha minus 1 mu plus 1 minus alpha 57. And that would give me my bias function. As a matter of fact, I could probably even go another step to get my risk function. I could go another step and maybe write this as alpha sigma squared over n plus alpha minus 1 mu minus 57. So if you go to the next page then, on to page 72. Yeah.
Are we supposed to square alpha when we take it out of the variance?
Yes. Thank you. Is that better?
Square the whole thing?
Yeah.
I thought you just squared the, like, whatever when you take it out. Alpha.
No, but this squared comes from this part. You're saying this part right here?
Yeah. And if we take the variance of mu,
Oh, yes. How could I? You are right. I am wrong. So variance of this should be squared. This should be squared. This should just get rid of this square root sign. Squared and squared and squared. Thank you. Did I?
Can you explain why you squared everything?
Which one? The squared here?
Variance.
For this part here?
Yeah.
For the alpha?
But
Oh,
not-
because when you take the variance of alpha mu to bring the constant out, you got to square it.
Okay.
From
But why do you not take out the end?
the n came from the variance of x bar, and that's sigma squared over n.
Okay.
That's where that one came from. That came from section 5.5. Actually, both of them came from 5.5. All right, so let's go ahead and graph the risk functions for each one of these. And which one would you take? If I had alpha to be equal to 1, my estimate will just be mu. And my variance turns out to be sigma squared over n. If I have alpha equal to 0, my estimate is 57, and my variance is 0. But my risk function is a little bit larger than that. This completely ignores the data. My risk function is basically how far I'm off with my naive guess of 57 off. And then finally, you could take the average of the two and take mu plus 57 over 2, and that then would be my average guess. It really all depends on how close my average would be. And if the answer was pretty close, then I'd have a pretty good estimate. If I'm far away from 57, I'm in deep trouble. So we kind of have to figure out what our estimates will be on that part. Okay, so we'll pick this up a little bit tomorrow and a little bit on Wednesday. Again, we're trying to figure out what statistical estimates we will use to estimate our parameter. Have a good November 2nd. Hope you had a good All Saints Day and celebrated those that came before you. Heroes of the faith. Josh? Gabe?
Right now is probably the worst time right now. We probably have like 5-6 guys.
From lacrosse?
No, it's not. It's just
Dr. Case, this is mine.
So we've got a couple guys in CM.
Alex?
Yeah.
We had one guy get it, but he wasn't around with us for a couple days because it was like over a weekend, so he didn't get that one.
Oh, really?
Dr. Case, do you ever have my stats?
What was that?
My exam.
Do I still have it?
Not an issue.
I like it because it's,